Hi everyone and welcome to this my video on cubic functions of the form y equals a in brackets x minus h all cubed plus k. Long title, yes, and not great when it's got a formula in it. My name's Darren from Maths Guru. Thank you very much for joining me. Now you said where, and I said Maths Guru, maffsguru.com. Thought it was funny in 2013. Now all I do is spend my life just spelling it. That's okay. If you can do me a massive favour before I start this video of subscribing, that would be great. Very few people subscribe to maths channels, and a lot of people say, hey mate, I love your content. It would be great if you could just let me know with that little click that actually you've watched. It really does mean the world to me. Right, that's the needy stuff over. Here is my learning objectives. I'm going to review them at the end of the video just to make sure we've ticked everything off, yeah? If you want to, please make sure that you just pause the video now and read over these. I'm not going to read them to you. It blows out the length of the video, but every video here is built on the content before, and hopefully this is going to be useful to you. Right, recap. We've already met a number of times the idea of transformations. I cannot tell you now that for mathematical methods in year 12, and again, if you have no idea outside of Australia what I'm talking about, don't worry about it. This content is equally valuable all over the world. But transformations are massive. Being able to take any function, all right, or a range of functions and move them and dilate them and reflect them is massive. Being able to take a function and do that is huge. 9 chapters worth, in fact, if I remember rightly, in the Methods 3 and 4 course. So getting used to this is great. Practice makes perfect. Seriously, the more you do this, the better you will get. And it is a huge part of the course. It seems silly not to actually learn it. Now, there is one rule to bind them all. I was going to put a picture of Gollum here, there, but I decided not to because you all think I'm probably mad enough. But the point of it is, there is a rule. That rule there is a particular form, a general form of a cubic function that we can actually use that will show us a horizontal translation, a vertical translation, and a dilation. And you're going to say, why is that useful? Well, go back to quadratics and completing the square form. Why was completing the square form really useful to us? Because it told us our turning point, yes? And once we knew the turning point, we could find my axis of symmetries, we could find all sorts of stuff. So in many cases, trying to manipulate functions to have them in a particular format makes life easier when we sketch them. Now, plotting graphs is a thing of the past. We don't plot graphs anymore. We sketch them. And to be able to sketch graphs, you've got to be able to show working out to find particular points, right? Axis intercepts, maximums and minimums, all of that is coming up. Now, when we take a basic cubic, and understanding what the shape of particular graphs are is really important. So the cubic graph is here, yes? It goes up, it sort of plateaus out, it goes back up again, yes? And this point here, it goes through 0, 0. So understanding that, really important. Also, making sure that you understand that this goes through 1, 1, and minus 1 is also important. So in an exam, you would be expected to put on any particular points that are important. Yes, so in this situation, I'm going to put through my axis intercepts. What do you mean axis intercepts? Well, anything that cuts through the x-axis and the y-axis, I'm going to put on. So there we go. So that's my axis intercept 0, 0. And also I'm going to put on a couple of points because when I translate these, I want to show people, hey, that point 1, 1 has made me move to, I don't know, 2, 1 or 1, 2 or something along those lines. Now, when you reflect the graph of y equals x cubed in either the x-axis or the y-axis, it ends up looking exactly the same. All right. Now, what does that mean is that that reflection there is if I reflect this in the x-axis, I get that. If I reflect it in the y-axis, I get that. Why? Well, if you remember, we can substitute in negative signs. We can take the whole function and make it minus. So what I'm saying here is that there is y equals minus x cubed. That's where I've reflected it in the x-axis. I've taken the whole function and multiplied it by minus 1, right? I've made all my y values negative, whichever way you want to remember that. Alternatively, if I reflect it in the y-axis, he says, when I reflect it in the y-axis, what do? I replace x with minus x. Yep. Now, what happens there is if I was to do minus x times minus x times minus x, what would we have? We get x times x. Sorry about that. We get x times x times x, which is x cubed. A minus times a minus is a plus. A plus times a minus is a minus. And there we go. So we end up in the same thing. So believe it or not, all of that hard work suggests that this here and that there are exactly the same. Now, if you want to download these lesson notes, head over to mathsguru.com, sign up, free to sign up, and you can download these lesson notes from this particular video and write all over them yourself. That's the whole point of summary notes. You do a brain dump now, and just before your exam, my advice is to then almost summarize your summary notes. And you're going to say, why on earth would I do that? Well, having done lots of past papers, which you're undoubtedly going to do at the end of the year, or particularly in year 12, you're going to remember so much more than your summary book, your initial summary book. So realistically speaking, you should be summarizing your summary book to put down the stuff you just can't remember. Those questions that trip you up, the formulas you can't remember, all of those type of things. If you want to walk in with a replica of the textbook, you may as well take the textbook in. Okay, so there's reflection in the X and the Y axes. And another important point here is the point of inflection. What on earth is a point of inflection? Right. When I was at school, we were taught that it basically is where you have a point of zero gradient. Now, at this point here, it is important to know that for the graph of y equals x cubed, that there has a zero gradient. It's flat. If I was to draw a tangent to that line there, it would be absolutely horizontal. So that has a zero gradient. Now, when I was at school, we were taught that so long as the gradient on the left-hand side of the points coming in and the points leaving had the same sign of gradient, then it was a point of inflection. The methods book is a little bit more interesting. That it says the point of inflection is found where the graph of a function changes concavity. All right, now when we have things like here, so there's concave down is that way, and concave up is that way. So what we're trying to say here is that this part of the graph is actually concave down. This part of the graph is concave up. Specialist maths, you deal with that left, right, and center. Methods, realistically speaking, we just mention it now. I think it comes a little bit later on in the course. But a point of inflection, I'm going to go with my version for the moment. It's basically, if I looked at all the gradients there, they're positive. Look all the gradients on the other side, they're positive. Let's just go with that for this moment in time. So knowing where points of inflection are is really, really important. Now, when we translate the graph of y equals x cubed, and I always think these graphs should look exactly the same, and you're going to turn around and say they're not the same. They are absolutely the same function, I promise you. This one here is the graph of y equals x cubed. So that one there is y is equal to x cubed. What's the blue one? Well, basically, as I say here, it's the graph of y equals x cubed plus 3. Yep, because I am taking every single y value and I am moving it up by 3. So if we look at this point here, we know this point here is 1, 1 because it's standard. So if I add 3 onto that, I get to 1, 4. And there we go. Notice the x value stays the same. It is only the y value that is changing. I'm taking every single point on this function and I'm moving it up by 3 places. Now that becomes massively important for sketches because that shows. But likewise, if we go to the idea I said earlier of actually highlighting or marking a point, there's 1, 1. If I now do that as 1, 4, I'm showing my examiner that that point has translated up by 3 in a vertical sense, yeah? So vertical translations up and down. What am I going to deal with next? Oh yeah, horizontal translations. And again, here, that is the graph of y equals x cubed. That's my base graph, as I like to call them, because that's where I'm starting from, right? But I'm now going to move it one place to the right. And if you remember, counterintuitively, when I move to the right, what goes inside my bracket is the opposite. So I'm expecting to put a +1 in there. It isn't. It's in fact -1. So my blue graph in this situation has the function y is equal to x minus 1 cubed. Right, so x minus 1 cubed. Now, if I'd had a number on the end of this, again, we can start combining things. That would have been a vertical translation. Do you see where I'm working towards? Yes. So again, in this situation, I would have put my point here as 1, 1. Unfortunately, I've knocked it off of my graph. But over there, I'd put my other point of 4, 1. If I had 4 on my graph, which I don't. Try that one again. He said, getting all tricked onto that one. It's not. I do actually have that point on the graph. It is in fact 2, 1. Oops. I still was stuck in the fact that I was moving this 3 places from the previous example. All right, so there we go. So I put that point on there. Let's do a dot to say that I know that I have now translated that 1 to the right. And in exams now, believe it or not, you can actually say left or right, all right? You don't need to say units parallel or whatever else, the x or y axis. What have we got next now? Right, sketch the graph of that function there. Now, first things first, we'd be looking for base graphs. What is my base graph here? Well, it's that floaty 3, which tells me it's a cubic. Now, what I tend to do on the side of my paper is very quickly draw a cubic. That is a pretty ropey cubic. So again, I'm going to draw a cubic like that. Now, a sketch has to be close to the actual thing. You can't just draw any old sketch. Examiners are looking for it to look close to what it should be. So my standard graph has a value here of 0, 0. It's got one there of 1, 1. It's got another one there of -1, -1. We're good to go. Sketch the graph of the function. Now I need to look at it and go, well, what's happened? We're looking for patterns. Everything I do in methods is looking for patterns. I've got this -2. Ah, well, that's okay because I'm moving 2 to the left, yeah? 2 to the right is counterintuitive. So I now know that this thing here is going to move 2 places that way. Notice what I'm doing. I'm putting a visual representation for me, an arrow with a 2 to the right. I'm not drawing it yet. I'm just trying to work out. +4. What does that +4 on the end mean? Ah, well, anything on the outside is a horizontal, a vertical translation, and it works in the same direction. So I'm going to go up by 4. Hurrah, he says. All good? So basically now, what can I do? I draw a line. I draw another line. Well, my points that I have these points here. So I can automatically use my ideas there to say, well, 0, 0 is going to have 2 moved that way and 4 up. So 0, 0 is going to become 2, 4. So let's do that as 2. Let's do that 4. There we go. So that's now my point of inflection. That's where that's going to move to. My 1, 1, I'm going to add 2 to the x value, which is 3. 4 to the y value, which is 5. So 3, 5. So that's going to give me my value there of 3, 5. What about this -1, -1? Add 2 is going to give me 1. Add 4 to that is going to give me 3. So I want 1, 3. There we go. So it's my 1, 3. Awesome. Fabulous. Can I now draw this on? Well, pretty much. I think I can go like this. That's got to be flat line. That's got a bit of a problem. Where's it going to cross my intercepts, my axes? Well, guess what? You got to actually find them out. So using the maths that we now know, and that we've done loads and loads of times with quadratics, you've now got to find your axis intercept. So I'm actually going to delete that for a moment so I can look at it a bit better. And how do we do that? Well, the easiest one is to find the y-axis intercept. So my y-intercept is given when x is equal to 0. So therefore my y-intercept is going to be, right, let's put 0 into here. 0 minus 2 is -2. Negative 2 cubed is -8, plus 4 is going to give me -4. So my y value there is actually going to be -4. Right, so that basically is going to be down here. So there's my -4. What about my x-axis intercepts? Well, that's going to be when y is equal to 0. So I want y is equal to 0. So I get it 0 is x minus 2 cubed plus 4. All right, so take away 4 from both sides. Minus 4 is equal to x minus 2 cubed. And so continuing here, bearing in mind that's supposed to be a 3, let's make that look like a 3. And again, handwriting is really important. So take the cube root of both sides, cube root of -4. A lot of people go, you can't have the cube root of -4. Oh, yes, you can. And that gives you x minus 2. In fact, we don't need those brackets anymore. And so x is going to be equal to 2 plus the cube root of -4. Now, you may be wanting to dive for your calculator at this point and work out what that is as a decimal value. Don't. In an examination, you will be expected to do answers as exact values unless otherwise stated. Right? So exact values, leave it with the square root sign. Doesn't matter how ugly it looks, we'll leave it with the square root sign. So what have we got here? So my x value when y value, so that there is going to be, and I'm running out of space, I'm going to do 2 plus the cube root of -4, 0, and then I've got my point here, which is 0 minus 4. Now, trying to draw this is going to be difficult. Why is it going to be difficult? Because my axes weren't necessarily as wide as I could have made them. That's okay. It's not a problem so long as I now try and make this go. I'm going to start it from the bottom, up through the points, flat line there if I can, and then up. I'm going to draw some arrows on the end of these here, just to show the examiner that I know that they go to infinity and beyond. Is that a great sketch? It's not going to win any awards, but the important part here is that actually we are showing here our working out, right? And that's what's going to get you the marks, the graph and the working out, showing your coordinates, doing what you need to do. Right, now I'm going to compare some graphs of x cubed and x to the power of a third. There are so many graphs you need to be able to remember, all right, and get the basics of for this particular course, all right. So which one of these is the graph of y equals x cubed? Well, hopefully if we do this here, there's my graph of y equals x cubed. Marvelous. We know that it goes down and then up. Right, what is this x to the power of a third, though? That's basically the cube root. So again, just in case you're interested, that's the cube root of x. Y equals the cube root of x. What do we notice with the cube root of x? It sort of comes along, and then it goes up, and it goes along there. Oh, that's interesting. What I'm now going to do is actually put on the line y equals x. So here is my line, y equals x. And what we find out is that those two graphs seem to intersect at that point there, and that point there. All right, they have similar points of intersection. And the reason being is, well, basically, I've taken the graph of y equals x cubed, and I've reflected it in the line y equals x. Now, when we do that, we end up what we call the graph's inverse. Massive topic if we haven't already done it, comes really, really big later. So basically, these graphs here are inverses of each other because I've taken one and reflected it in the line y equals x, and I've got the other one. And this is a huge topic that will come later. But it's also important to notice that the graph y equals x cubed is a one-to-one function. And one-to-one functions can have inverse, all right? So a one-to-one function will have an inverse function, but there are things also as inverse relations or relationships, which we'll come to at another time. So now it's going to be important to realize what the graph of y equals x to the power of a third looks like. Okay. Sketch the graph of y equals x minus 1 to the power of a third minus 2. Okie dokie. So here we go again. Let's draw some basic axes, and let's remember that the graph of y equals x to the third looks roughly speaking like that. What have we got here? We've got a point there of 0, 0. Do I know any points on this graph? Let's have a look. Let's go back. Do I have any points on this graph? Oh yeah, the point 1, 1 and minus 1, minus 1. Oh, awesome. So that's still 1, 1. And that point there is minus 1, minus 1. Hurrah! We've got the basic graph. There's my base graph. Let's have a look and see what's going to happen. X minus 1 inside. What's that actually going to do? Translate into minus 1? Ah, counterintuitive. I'm actually going to move it that way again, one place. So I'm going to put on here, one place, and then the minus 2 on the end here. What does that minus 2 do? Oh, I'm going to move my whole graph down by 2 places. He says writing in highlighter. So down by 2. Right. What does that mean? Well, the first thing I'm going to do is I'm now going to work out where all my new points are going. So 0, 0. So it's going to become 1, negative 2. This one here is going to become 2, negative 1. And this one here is going to go 0, 1, minus 2, minus 3. So we're taking 2 away from each of those. And there we go. So those are my new points I'm going to be plotting in a moment. But what else do I need to work out? My x-axis and my y-axis intercepts. Do I need to work out my y-axis intercept? Why? Because it's already done for me. Anything that starts 0, is already my y-axis intercept. So thank you very much for that one. I've got that one. Let's hopefully work out what my x-axis intercept is, which is really the harder one. So that's going to become 0 is equal to x minus 1 to the power of a third minus 2. Add 2 to both sides gives me 2 is equal x minus 1 to the power of 1/3. How do I get rid of a cube root? We cube everything. Okay, so that's going to give me 8 is equal to x minus 1. Oh, that was nice. So x becomes equal to 9. So when y equals 0, x is equal to 9. So 9, 0 is where this thing is going to cross my x-axis intercept. Right, let's actually have a look and then try and draw some decent axes. All right, so we got a crossing point at 9, 0. So there's 9, 0. What have we got here? We've got this point here is going to move to 1, -2. So 1, -2 is there. So we've got 2, -1 is here. What else we got? 0, -3 is going to be here. All right, so again, 0, -3. I'm running out of room for my points. Do we think we got everything we need? I should Coco. So what do we do now? Let's change my color again. So my -1, -2 is where it's going to go vertical for a very short period of time, or for a nanosecond. That's going to go then through here, and then that's going to curve through here and go that way. And again, trying to draw that in this pen is not great, but it gives the general idea of that's ultimately what my curve is going to look like. Probably I could make that do that a little bit better. Now again, when you draw these things in the exam, make sure you draw them in pencil. Yeah, because if you get them wrong, then at least you can rub them out. Never draw them in pen. And your examiners are looking for smooth curves. So trying to work out how to draw these smoothly is also really, really important. Find the inverse function of, function notation. Now again, this becomes critically important. Understanding what this notation means is huge. So you've got a function defined as f, all right, where real is mapped onto real. Again, the real numbers means it's, you know, that's its domain. The first thing here is the most important to say, its domain. And here we go. Right, so when you work out the inverse of a function, I'm going to do y is equal to 2. X minus 4 cubed plus 3. What do we do now? When you want to work out the inverse, what are you doing? You're reflecting it in the line y equals x. It means that all my x values become y values, and my y values become x values. Or we just swap the x and the y around. We can do that. So x becomes equal to 2, y minus 4 cubed plus 3. Now, obviously, in this situation, because we want to find the equation of the inverse, then what are we going to do? Find the inverse function of, so we're going to say, we want to find, what do I want to find? Y on its own. So the first thing I'm going to do is I'm going to move the positive 3. I'm going to take away 3 from both sides. So x minus 3 equals 2, lots of y. Make sure that's a minus cubed. Right, divide both sides by 2. Let's get rid of that one there now. So I'm going to get x minus 3 on 2 is equal to y minus 4 cubed. Let's get rid of the cubed to make it cube root. So we are now going to have x minus 3 on 2 with the cube root is equal to y minus 4. And finally, we are going to add 4 to both sides to give me. So y is equal to 4 plus the cube root of x minus 3 all on 2. Right, there we go. So now we've got to write that in function notation because it wants the inverse function, yes? So will this actually still have a domain of real onto real? Yes, there's no change in that situation. All right, my domain will become my range will become my domain. But for my original function for a cubic, it's defined on both of them, right? There's nothing that it can't be. So I'm now going to say that therefore, f to the minus 1 colon real mapped onto real, comma, f to the minus 1 of x is equal to, and I'm going to run out of room, so let's see if I can move that around somewhere. Actually, let's move all of this over. Bear with me. Let's move all that over to give myself some space. Yep. Is equal to 4 plus x minus 3 on 2 with a little cube root there. Yeah, and there we go. And again, please be very careful in exams because when they ask you for a function, write it in function notation. I know in a previous school we wrote a SAC and kids lost marks every single time they didn't write it in function notation because that's so important. Right, there we go. Learning objectives review. Let's have a look back and make sure now. I know I didn't read them at the beginning, but let's make sure we got what we were supposed to do. First one, understand how we can transform graphs of the form y equals x cubed using dilations, reflections, and translations. Yes, we've done that. We looked at the reflections in the x and the y axes, dilations from the x and the y axes. Again, that just stretches the graph. Translations, we looked at those as well. Know what the general form of a transformation of a cube looks like. We've got that. and understand what a point of inflection is, we are done. Oh my goodness. Thanks so much for watching. If you can, subscribe to my YouTube channel, that would be huge. Thank you so very much. Lots more videos over on maffsguru.com. Downloadable lesson notes, all the stuff I've been writing on behind me, and so much more. Past exam papers, online exams, all sorts of stuff for you to be able to do. But other than that, I'm going to call it a day. Take care, and I'll see you again.